Sometimes you see something that's so simple, yet completely mesmerizing. What you're looking at is this beautiful piece of kinetic art, a structure that just flows with an almost magical quality. But what you're really seeing, it's elegant geometry in motion.
So it all starts here, as this compact little starburst, right? It's a chain of these colorful, interconnected arms. Each piece looks pretty straightforward on its own, but when you link them all together, well, they're holding a secret. Because with just the slightest push, the whole thing glides open. And it doesn't just get bigger, it expands with this incredibly fluid, seamless motion. Every single piece is moving in perfect harmony with all the others.
And it all resolves into this, a perfect circle. It contracts just as gracefully, like a breathing mechanical loop. And this isn't some approximation, it's a geometrically perfect circle every single time. Which, of course, brings us to the central puzzle. So, how does this even happen? How can a collection of what are basically hinged sticks, which you'd think would just expand in a line, somehow manage to curve back on themselves with such incredible precision? Well, that's exactly what we're going to figure out.
To really get how our circle works, we first need to look at something that doesn't work, the traditional straight bar linkage.
Okay, this is the basic building block. You've seen this a million times, right? It's a simple scissor mechanism, just two identical straight bars pinned right in the middle. You move the ends, they pivot open and closed. Easy enough? But here's the key geometric rule. No matter how open or closed it is, those four endpoints will always define the corners of a perfect rectangle. Always. That's locked in by the geometry.
So what happens when you chain a bunch of these units together? Well, you get familiar things, like a retractable gate or a scissor lift. They expand and they contract beautifully. But notice the movement. It's purely linear. It only gets longer or shorter in a straight line.
And that is the fundamental problem. The geometry of the straight bar literally traps the whole linkage in a line. It can never, ever curve back on itself to form that amazing circle we saw at the beginning. So, how do you break it out of that straight line?
Well, the solution is, honestly, breathtakingly simple. It all comes down to introducing one small change, a beautiful, elegant bend.
On the left, you see our old friend, the straight bar. And on the right, well, that's the hero of our story. The only difference is that each arm now has a very specific, permanent bend in it. And this single, deliberate twist, it unlocks an entirely new dimension of movement.
It's like the source material says. However, if we bend the bar a little, the math magic happens. We get a surprise of a retractable circle. And it really does feel like magic, but I promise you it isn't. It's just very, very clever math.
So let's pop the hood and dig into the mechanics. Let's see the mathematical principle that actually forces this circle into existence.
Here's our single unit again, but this time with the bent bars. Just look at the new angles and the new relationships that are forming between the pivot point and the end points. The secret to the entire circle is hidden right here in this new geometry. Okay, to understand this, we just need two key terms. Don't worry, they're simple. First is the bar angle, we'll call it phi. That's just the fixed, unchanging angle of the bend in each bar. Second is the central angle, we'll call that alpha. That's the angle that the two outer arms make when you trace them back to a single point. And here it is. This is the breakthrough. There's a fixed relationship between those two angles. The math proves that the central angle, alpha, is always 180 degrees minus the bar angle phi. It's a direct, unbreakable link. So here's the aha moment. The crucial point is, because the bend in the bar is fixed, it's not changing, that means the central angle is also fixed. It's constant. As the mechanism opens and closes, that angle never ever changes. Each unit claims its own fixed slice of a pie, which forces all the other units to arrange themselves around a common center point. The linkage has no choice but to form a perfect circle.
And this table shows you exactly how it works in practice. Let's say you make your bars with a 150-degree bend. The formula tells us the central angle for each unit will be 30 degrees. So to make a full 360-degree circle, you'll need exactly 12 of those units. If you bend the bars even more, to 160 degrees, your central angle gets smaller. It becomes 20 degrees. Now you need 19 units to complete the circle. The bend directly dictates the final design.
Okay, so now that we get the math, let's look at the beautiful results. This is where the cold logic of geometry really transforms into something expressive and interactive.
This one simple principle allows for these stunning kinetic sculptures. The art isn't static. Its beauty is in the movement itself, that transformation from one state to another. all governed by that one elegant geometric rule. It also leads to these incredible interactive designs. These aren't just objects you look at. They're things to be touched and played with. They actually invite you to feel the geometry, to experience that smooth, predictable motion that comes from such a simple principle.
And this makes it an incredibly powerful tool for STEM education. All of these abstract concepts like angles and linkages and geometric constraints, they suddenly become tangible. You can literally hold the proof in your hands. It's math you can actually see and feel. So, let's just recap what we figured out here. First, a simple, deliberate bend is all it takes to transform a rigid, linear motion into fluid, circular motion. Second, the whole geometric secret is that constant central angle. And finally, this principle is just a perfect example of that beautiful space where art, mathematics, and engineering all come together.
Which really just leaves us with a final thought. We unlocked the magic of a perfect circle just by adding a simple bend to a straight line. It really makes you wonder, what other extraordinary secrets are hiding out there in plain sight, just waiting for one small, clever twist?